The ligand substitution reactions in octahedral complexes proceed almost always via the interchange mechanism. That means in the intermediate structure, the transition metal center forms a partial bond with the entering ligand. The bond between the transition metal center and the leaving group is partially broken. The interchange mechanism can be associatively activated or dissociatively activated. Associatively activated means the first step of association is the limiting step. Dissociatively activated means the second dissociation step is the rate limiting step. But either way, it's called interchange mechanism. Either way, you have a partial bond between the transition metal and the entering ligand, and also a partial bond between the transition metal and the leaving ligand. Why don't those ligand substitution reactions in octahedral complexes go through association mechanism or dissociation mechanism? Well, this is because the steric effect hinders the associative mechanism. It's hard to imagine the transition metal forms 7 whole bonds with 7 different ligands. And also in the dissociative mechanism, you have to break a metal ligand bond completely, and that's disfavored energetically. So let's look at section 21.5, rate laws and their interpretation of the Eigen-Wilkins mechanism. So subsection A, the Eigen-Wilkins mechanism. In this mechanism, Eigen and Wilkins propose that it's possible for the entering ligand Y to form a intermediate structure with this ML6. And this means this Y is close enough to the transition metal center to form a partial bond. So again, this Y is really close to the transition metal center. All right, how close? It could be only 2 angstroms, 3 angstroms. And this curly bracket means, well, again, these two are really close to each other to form one additional bond between Y and M, although it's a partial bond. And in this Eigen-Wilkins mechanism, they assume this reaction can reach fast equilibrium. That means the forward and the reverse reaction rate constants are both large, really large. And that means the reactants, this two, and this structure, the intermediate structure, are always at equilibrium. So we can define a pre-equilibrium constant. In this case of E. E stands for Eigen-Wilkins. And we put the concentration of the intermediate on top, the reactants on the bottom. So this equation is always approximately true throughout the entire reaction. And then let's look at the second step. This intermediate decompose into the product plus a leaving ligand L. Assuming this is the slow rate limiting step, and then this interchange mechanism is dissociatively activated because the second dissociation step is the rate limiting step. Overall, the reaction rate is determined by the rate limiting step, so it's going to be just K times the concentration of the intermediate. All right, so over here, this K is the rate constant for this first order reaction. And now let's do some mathematical derivation. So this is the total concentration of the transition metal. It exists in the solution in two different forms, this way or this way. Okay, two different forms at the beginning of the reaction. All right, assuming there's not much of the product. Okay, at the initial stage of the reaction, the metal exists either in this form or in this form at the beginning of the reaction. And also we have another equation. From here, we know ML6 is equal to this intermediate concentration divided by Ke times 1. So over here. From here, this equation to this equation, it's simple algebra. Now we have this intermediate concentration plus this ML6 concentration, which is this. I'll plug this in. Okay, is equal to the total concentration of the metal. And then we can derive the expression of the concentration of the intermediate. So again, over here, Y is really close to M, close enough to form a partial bond. The concentration of this is M total over 1 plus the reciprocal of K sub E times Y. All right? And we got this equation here, from here to here, both the top and the bottom of the fraction are multiplied by K sub E times Y. So that's Y. Okay. Oh, this should be italic. And now we have the reaction rate. It's equal to this K times the concentration of the intermediate. And we have the expression of the concentration of the intermediate. We plug it in. So it's going to be just K times this whole thing. So it's going to be K times uppercase K sub E, the eigen equilibrium constant, times the total concentration of the metal, times Y over 1 plus K sub E times Y. If you have some experimental data of this reaction rate, given different concentration of Y, we can do some analysis. All right, but look, this R is not linear with Y. Okay, so you can't just plot R versus Y directly. One very simple trick is to take the reciprocal of both sides. So you get 1 over R is equal to the reciprocal of this. Why do we need to take the reciprocal of this? Very simple. If you have a sum on the bottom of a fraction, you can separate this two. But after you take the reciprocal of the fraction, the sum appears on the top as the numerator. And then you can separate this two. So we separate this two. So it's going to be 1 over this whole denominator plus Ke times Y over the whole denominator. And Ke and Ke cancel, Y and Y cancel. That's why the second term is simpler. Okay? And now if you look at 1 over R versus 1 over Y, it's linear. It's linear. What's the slope? The slope is 1 over K sub E times M total. That's the slope. What's the intercept? This is the intercept. As long as you make sure you use the same concentration of metal at the beginning, the total concentration of the metal is the same. And then you do the experiment. You change the concentration of Y. Y is the entering ligand. You measure the reaction rate. And then you plot 1 over R versus 1 over the concentration of Y. And then you get the slope. The slope is this, 1 over K, Ke, M total. This is the slope. What's the intercept? This is the intercept. And then the intercept divided by the slope. Okay? You get K sub E. This is how you get this Eigen-Wilkins equilibrium constant for the first step here. This is a fast equilibrium approximation, and we can determine this constant here. All right. So when you do data analysis, it's not always y versus x. You measure two variables. It's not always directly the first variable versus the second variable. Sometimes you need to manipulate the data first. In this example, it's the reciprocal relationship. If you have taken chemical kinetics, you learned this Michaelis-Menten mechanism, you realize that the same thing. You have 1 over the reaction rate is linear to 1 over the concentration of the substrate. It's the reciprocal plot in this kind of situations that gives us useful information. Now let's look at this equation again. It's possible for this y to be small enough that on the bottom, this Ke times y is much smaller than 1. For example, if Ke times y is 0.01, or even smaller, you can neglect this term. And R is equal to K times M total times y. That means when the concentration of y is really small, this reaction is a second-order reaction. The rate is proportional to the concentration of the metal and also the concentration of y. Well, what if you have a very large concentration of y? Large enough that this Ke times y is much greater than 1. Let's say Ke times y happens to be 100 or more than 100. And then you can safely neglect this 1. And when you do that, Ke and Ke cancel, y and y cancel. The reaction rate constant, this reaction is going to be the first order reaction. The reaction rate R is approximately this K times this M total. So it's just proportional to the concentration of metal. And this is first order. So again, really it depends on the concentration of Y. When the concentration of Y is large, first order. It does not depend on the concentration of Y. It's pseudo first order. When the concentration of Y is very small, okay, it's pseudo second order. R is proportional to the concentration of Y. It's also proportional to the concentration of the metal. This is summarized here. It can be second order. It can be first order. If you have taken chemical kinetics, if you remember the Lindemann mechanism for unimolecular reactions in the gas phase, you will learn this as well. Okay, so it's just a unimolecular reaction from A to P. But for A to be converted to P, A needs to accumulate enough energy via collisions. So A may collide with other A's, and then the energy can be transferred between the two colliding bodies. And when one A accumulates enough energy, it may be converted to P after overcoming the energy barrier. So in that case, when the concentration of A, the reactant, is really low, it's second order, because the collisions between molecule A's are the rate limiting step. However, when the concentration of A is really high, so the rate limiting step is from A to P. Okay, it's the conversion from activated A to P, because you need to overcome a large barrier. And then in that case, it's going to be the first order. Subsection B, the Fuchs Eigen Equation. The Fuchs Eigen Equation is used to estimate the pre-equilibrium constant K sub E for the Eigen-Wilkins mechanism over here. Eigen-Wilkins mechanism assumes there's a fast equilibrium between the reactants and the intermediate. Okay, so this is the equation, the Fuchs Eigen equation. Let me explain this. This apparently is the equation of the volume of a sphere with a radius a. So a is the encounter distance between this transition metal complex and the entering ligand Y. Okay, how far away this Y is from the transition metal center. Okay, this n sub a is simply the Avogadro constant. It's about 6 times 10 to the power 23. All right. E to the power of negative v over kBt. If you took the physical chemistry series, this is the so-called Boltzmann distribution. Over here, this V is not the volume. This V is the Coulombic potential energy here between the two reactants. So between the entering ligand Y and the transition metal complex, okay, between these two. The reason is very simple. If these two attract each other, all right, it's favored energetically, okay. And then you plug in the attraction here. Attraction is negative, negative. That becomes positive. You get a factor larger than 1. That takes the attraction into account. What if the two reactants repel each other? It's rare, but just to make it this analysis complete. What if the two reactants repel each other? What if the ligand repels the transition metal? Then the repulsion energy is positive. This V is positive, and then this exponential function is less than 1. All right. If they repel each other, it's less likely for them to form the intermediate. Okay, this again is just to make my analysis complete. It almost never happens. I have never seen a case in which the ligand, the entering ligand, repels the transition metal complex. Okay. Oh wait, it's possible. So it's possible for this transition metal complex to bear negative charges. And the entering ligand also bears a negative charge. Sorry about that. And I can give you an example now. Tetrachlorido platinate with an oxidation number of 2 on platinum. In this case, this transition metal complex bears a negative 2 charge. And then let's say we have a entering ligand, bromido minus, which also has a negative charge. In that case, the transition metal complex and the entering ligand repel each other. In that case, this exponential function is less than 1. And then you have a smaller k sub e. Now, if you look at this expression, okay, we need to explain why it looks like this. The equation of the volume of a sphere multiplied by the Avogadro constant. Okay, I'm going to give you a proof for uncharged species. So that means let's assume the transition metal complex is neutral, the entering ligand is neutral. All right? In that case, this Coulombic potential energy is just 0. We can ignore this exponential function. And then we can focus on this part. So why is this Eigen-Wilkins equilibrium constant equal to this expression? Well, here's our derivation. We need to know the ratio between the concentration of Y that's in the intermediate structure and the total concentration of Y. Okay? Well, actually, this is free Y, but usually the concentration of Y in the intermediate is a very small percentage of the total y. So we can have this equation hold true approximately. So this y is approximately y total. Okay. And now let's imagine this y in the solution is distributed evenly. And then that means, well, over here, we just need to somehow find the number of y molecules found in the intermediate structure, right? And then divided by the number of y molecules in the entire solution, right? And also, we assume the concentration of y is even inside the entire solution. No matter y is a free solvent molecule or y is really, really close to the transition metal complex. All right. So statistically, we're going to say, well, on top, we just need to count the number of Y ligands that are close to ML6 or in the vicinity of ML6, right? On the bottom, we need to count the total number of Ys. Now, assuming the concentration of Y is the same everywhere inside the solution, then this top over the bottom is equal to, well, the volume of the vicinity area surrounding this ML6. All right? And on the bottom, it's going to be the total volume of the entire solution. All right? And then on top over here, let's look at the just one ML6. Okay? Close enough to Y. So we do have a parameter A here as the encounter distance. So this is the distance between Y and the transition metal center. So if we do this 4/3 pi A cubic, that's going to be the volume of the vicinity area of this transition metal center. That may contain a Y. Okay? So if you do this, you get just the volume surrounding the transition metal complex that may contain this Y. And then we need the number of ML6 complex. Okay, the number of ML6 is the number of moles right here. This is the number of moles of ML6 multiplied by N sub A. That's the number of ML6. This is a huge number. And assuming we imagine a sphere surrounding each ML6 complex, and that sphere has this much volume, okay, and that will give us the sum of the space surrounding each ML6. That's big enough to contain this Y. All right, so that's on the top. Okay, and that gives you the volume that this Y in the intermediate may occupy. On the bottom, that's just all Y ligands, either solvent molecules or the ligand intermediate, just everything, and that's the total volume. So again, on top, that's the volume this type of Y ligands occupy. On the bottom, that's all Y ligands occupy. And then V total and V total cancel. And we have this expression left over here. And remember the definition of the Eigen-Wilkins equilibrium constant. It's this guy divided by Y divided by ML6. And therefore we have this expression as the Eigen-Wilkins equilibrium constant. So we just derived this part. Okay. And again, the second part, in the right-hand side of the equation, this exponential function takes the Coulombic potential energy between the entry ligand and the transition metal complex ML6 into account. Okay. Now here's a numerical example. Let's say the transition metal complex or the entry ligand is uncharged, and then there's just no Coulombic attraction, no repulsion. Then this V is 0. You can ignore the exponential function. And we have this K sub E to be 4/3 pi a cubic. So this is, again, the sphere surrounding 1 ml6. And this sphere may contain Y in the intermediate structure. And then multiply by the Avogadro constant. Now the value of A is given to you. The encounter distance is 200 picometers. This is also 2 angstroms, or 0.2 nanometers. So this is just a rough estimate of the length of the partial bond between the entering ligand Y and the transition metal. And then we plug in all the numbers, okay? 4 pi over 3 times, this is the encounter distance A to the power of 3 times the Avogadro constant, and we get this K sub E over here. This is the SI unit. This is the, non-SI unit, but commonly used unit. What if you have both reactants, the entering ligand and the transition metal, both are charged, and they have the opposite charge? Okay. Let's say the ligand has a -1 charge, the transition metal complex has +1 charge. The value of K sub E is increased significantly by a factor of 36. How come? Well, it's just very simple. It's e to the power of -e over kBt with the Coulombic charge. If you have taken general physics, the Coulombic potential energy between two charges in vacuum is Q1 times Q2 over 4 pi epsilon r. But now if it's in water, okay, this epsilon r, we need to take that into account. It's 78 for water. And then we do the calculation, and then over kBt. We get 36. So this K sub E, the Eigen-Wilkins equilibrium constant, is increased by a factor of 36. I want to tell you how I got this expression here. This is actually 1 atomic unit is equal to 2.6 million joule per mole. So I'm actually doing the calculation using atomic units. In atomic units, the charge of 1 electron is -1. So we have just 1 times 1 over, and in atomic units, 4 pi epsilon is 1. So I don't have to worry about 4 pi epsilon. And R is 2 angstroms. So this is to convert 2 angstroms into 2 atomic unit of length. That's 2 over 0.529. Because 1 atomic length is 0.529 angstroms. So I'm converting angstrom to atomic unit of length on the bottom, and on top, that's just 1 atomic unit of energy. Okay, that's the attraction between a +1 charge and the -1 charge. When the distance between the two charges is 1 atomic unit of length. So that's why I got this actual distance here. 78 over here, that's for water. And again, we're converting in the end the 1 atomic unit of energy to joule per mole. So in the end, this is in the SI unit. And I forgot to mention that I need to multiply the top by the Avogadro constant to get this. Otherwise, 1 atomic unit of energy is actually roughly 4.4 times 10 to the power of negative 18 joule. And then you need to multiply that by the Avogadro constant, and you get this 2.6 million joule per mole. And since I multiplied the top by the Avogadro constant, I also multiply the bottom by the Avogadro constant. And the Kb times the Avogadro constant is R, so I have RT there. And then you plug in all the numbers, you get 36. However, if you do not like to use atomic unit, that's fine. It's just Q1 is just 1.6 times 10 to the power of negative 19 Coulomb. Q2 is negative 1.6 times 10 to the power of negative 19 Coulomb. You need to look up the value of 4 pi epsilon. I think 1 over 4 pi epsilon is roughly 10 to the power of 10. I might be wrong. And then you look up the value of epsilon r for water. It's just 78. This is unitless. And r, you need to plug in over here 2 times 10 to the power of negative 10 meters. And the Kb, I think, is 1.38 times 10 to the power of negative 23 joule per Kelvin, and T is in Kelvin. So after you do that, you'll also get 36. But again, you need to look up the value of 1.4 pi epsilon. I just don't remember the value for that.